My name is Stephan Sahm. Thank you all for joining today. I'm the founder of Jolene.io and still since 2 years, I think by now, organizing this Julia User Group Munich. Every second month there's a speaker and another month there's like this introduction session with the formula law with Julia. Today with a little bit more code, a little bit more intermediate, but I hope it's still kind of introduction level. Okay, so what we're going to look at are a couple of examples from the scientific machine learning ecosystem. So there's definitely much more to it. So I will only pinpoint a few simple examples which I find particularly interesting and good to see that this all works together. But there's much more you can explore, especially because all these single parts which we're going to combine together, there's neural networks, there's differential equations, and there's probabilistic modeling. They they all are super expressive and you can use so much more. So the space and combinations between these is so huge, there's no chance to get this into a little condensed presentation. So we start with a little recap on neural networks. Then we go to just have a little intro to the differential equations with the famous example from the Lotka-Volterra equations, seeing some prey and some predators. Then we go into the SciML sphere. So first we do a differential equation within the neural network and then the other way around to have a neural network which models the derivative. Then I'm going to the probabilistic sphere because this is actually one of my favorite realms as well. So I've been in the probability theory and we see a combination here which very much fits what we've seen before, but now with the probabilistic add-on, and we see also how it can be useful. And lastly is a note on the symbolic regression capabilities of the data-driven DiffEqFlux package, but this should be very, very short. So my main background here are two tutorials which are out there. So you may have seen them, but this is kind of a combination between the two and a couple of bits before and after. And I have another list of references at the bottom. Okay, so let's start right into it. What is also a little bit different today than in other sessions, things may need a bit more time to actually run. So this is because we have a couple of more stuff to compute. Differential equations are usually heavy, but yeah, even with this single examples, I had execution times of a couple of minutes. So yeah, bear with me and be a bit patient, but I think it's still very much interesting and worth it. So we start by looking into the neural networks. As always, of course, you're free to ask questions, ask them in the chat or raise your voice. All is fine. And I'm having a look on the chat. I have it open as well. Yeah, so all works. So we import Flux. I decided to import it. Usually you would be using it like all the other packages, but just to make clear what is Flux and what is not Flux, I'm now using the import statement to not have anything else in here, so that the namespace is a little bit clearer, a little bit cleaner. So importing Flux takes already a little bit time, but let's go on. So what I want to introduce you is that with Flux, we can do learning, machine learning. And yeah, the generic principle is we define our loss function and take the derivative and then, stepwise we iterate through it. And for this, we just created a little dummy example. You can experiment with this and create something else. And my goal here is just, I have a couple of values coming in, I'm summing them up and check whether the sum is larger than half of the values. So very, very basic. And we generate some numbers. I have here now kind of 10 values per row. And then I'm computing the goal for every such value. So the for comprehension is surely known also by those not new to Julia, and this dot is the broadcast operator. So with this, we can broadcast any function on top of an array. We do this once for training and once for validation. And then we do a nice histogram plot, which is easiest explained by just looking at it. So now, especially the histogram is precompiled, and yeah, and soon we're going to see kind of our input data. We have only a few input data. So what takes time here is really not the computation, but the pre-compilation, the typical Julia thing. So there we are. We have a couple. This is our input data. So I'm just plotting the sum of all these input variables against kind of the class by histogram, the one and the other. And you see that we have a nice even distribution between them. So if you would be a totally stupid predictor, you would just flip a coin and say 50-50. This is probably your best chance. So we want to do better than 50-50. It's always good to know your baseline. And we do this now by just building a stupid neural network, but it should showcase what you can do. So the typical thing in neural network is that you have layers, and this is kind of supported by the flux chain function or constructor, where you have as many arguments as you want, which are then the layers. And each layer is just a function. So you may have used Flux and now this, but this is pretty cool. So you can really use any Julia you want. And it happens there's a couple of functions are predefined by Flux. And there's this famous dense layer where we have a dense neural layer, so a perceptron, which then goes from 10 neurons to 5 neurons, and using here a sigma activation function. And you have another dense layer which uses the default activation function from 5 latent neurons to output neurons, and then finally we put a softmax function on top of it, and stack this together with the flux chain. We can call this because chain is really more or less just like function composition, and combining all these functions together, we call this on a random element and get our softmax activation. So this is really, you can interpret this as kind of probability. So the neural network now says, with a probability of like 90%, this is class 0. Okay, so to get a bit more information what we are actually doing, there's a little accuracy function here where we use the one cold function. Just good to know if you do these classification problems, one cold and one hot are lovely helper functions which you want to use. So here we get this output, which is probability, into either 0 or 1. So this is then compared to our final. We again have a helper function which we then broadcast. So this is lovely Julia style. We take the average. Okay, and then we see kind of that when we started, we are near 0.5. So actually on the validation, we are worse. So we are worse than stupid. Let's fix that. And this is kind of the, let's run it. This is kind of a simple way how to train your network. And it is the most explicit. So we see kind of another method how you can use this. But let's go through it just for repetition. So we define our loss. I already told this. And we compare kind of our input covariates with our target value. And we use now the standard cross entropy, which is used for such classification tasks. We compute the output of our covariates of the x, just as before. Now just wrapped into the loss function. And we use the alternative, the one hot, and take kind of this category value, which is 0 or 1 in the y, and encode this as a one hot value, where the the first or the second cell then has 1 and everything is 0. So this is kind of the input which we need. So they are then both of the same kind, and we can apply the cross entropy. Use just a momentum optimizer. So there are different optimizers you can use, the Adam, stochastic gradient descent. Many different things. I think Adam optimizer is the most known. And then the flux setting, we have implicit parameters, which is very handy for neural nets with many parameters. So we call the params function from Flux on top of our model, and it extracts all the parameters within all the layers. So that's a nice implicit handling for us. And I think one of the only magics which Flux actually does. So all the rest you can easily write yourself. So now we train. We just have we go with a for loop, our training data, just zip it, and now for every value, for every row, we compute the gradient. So this is a flexible one. So here you can now then also plot stuff and so forth. And yeah, we need to compute the loss, and this is kind of the standard convention also. So this really should be the loss. So you want to get this close to 0. Yeah. So minimizing, maximizing is sometimes this plus minus problem. So this is always minimizing things. Yeah, this is the convention. Then we have our gradients, and we can call an update method, which then is specialized for the different optimizers. Optimizes the first argument, our parameters the second, and then the gradients for exactly those parameters. And this is it. So we just run this, and you can run it a second time, and see that we may improve even a bit further. So give it kind of a couple of tries, and it will improve further. So this is not optimal, despite this problem is so simple, because we made it a bit harder for the network. We said it should start with squaring everything. So this is probably very tough, but you can, if you want, you can easily now adapt this network and see how you can optimize the simple task. You can also imagine kind of another goal which you want to achieve and just see, okay, sometimes the problem looks so simple, but still neural networks, have a hard time learning it. Of course, this is also not deep. But so this was the little introduction to Flux, because we are doing a lot of learning today. And I wanted you to be up to date with the Flux ecosystem. So I have a little initial initial task for you to get back into Julia. We've been seeing a little histogram plot above, and it would be nice to see the performance of our network. So like whether it's really similarly clear cut. We see kind of really the one class is left, the other is right, or how it looks like for our neural network. So let's just give us a little time. Try this. Just for recap, so Jupyter Notebook, you probably all know. You can easily create new cells here. There's this plus button, and with this, you can then add a new cell below, and you can execute cells by pressing the run button or by pressing Shift Enter or Control Enter, like you like. Okay, so I'm doing it myself now, just to have a good thought on the timing. Might be a good start to just look what's above. And adapt it. Okay, so this is kind of the key part then. we don't have this target value in the setting, but we need to use our neural net somehow on top of our initial part. This is a little bit more advanced, as I warned you in the beginning. Yeah, and we can't do this comparison here because this is, yeah, just as we saw, this is a vector of 2 values, and we need to one cold encode this. We could use broadcasting for this, but in this part, it's easier to just use the for comprehension. And good thing about Julia is that it's usually not slower, but just same part, same speed. Okay, this would be my little try. Sure, of course. Oh, yeah. Okay, so this would be a kind of prepared solution. Yeah, so as you see, this is really not optimal. It makes sense that it's not a clear cut, otherwise you would have 100% accuracy. Yeah, but we see nicely that this is a smooth, yeah, kind of bell curve. Okay, so this was my little intro to get you back into Julia. So what was important here? We have this one code function, which is new. And yeah, but you've seen it above, where we can match our probability space to a concrete category. So we here specify which category it is, so 0 or 1. And this is important because, yeah, Julia has kind of a default value for starting counting the indices at 1. So the first index is 1, second is 2, so forth. And yeah, often this is quite handy, and sometimes it's not so handy. Yeah, so you have to be careful with this. And this one code is kind of one example of this, where you usually specify this concretely. And because of this, you can't easily use broadcasting. Okay, so we fall back to just having a for comprehension. Otherwise, you would get difficulties with the broadcasting here. You can define a helper function, and that's fine. Yeah, or yeah, do it like this. Okay, so that was it. Then let's jump ahead for some differential equations introduction. And yeah, okay, of course, always if you have questions, please raise your voice or write in the chat. So what we're going to look at is the most famous introductory example. Yeah, hence there's also a couple of material for it. And now we have kind of this notebook which summarizes it a little bit. I'm executing already the first cell because it takes a bit longer. Not really, actually. Okay, so it just only defines the problem, and I'm executing the second cell as well. It now solves the problem and precompiles the code for it. So what we're going to see here in a second are the populations of preys and predators. Let's think of rabbits and foxes. And the differential equation is quite simple. So the rabbits are X and the foxes are Y. And we model the differences in rabbits like the following. It's easily comprehensible. I also wrote it here kind of below. So we assume that rabbits spread and become more rabbits by just waiting. So we see an increase on the number of rabbits themselves by just a growth factor. And we see a decrease here. So all the parameters are meant to be greater than 0. We see a decrease by all the interactions between rabbits and foxes. And for foxes, it's just the other way around. We see that the foxes population is really healthy and spreading if there's a lot of interaction, if there are a lot of rabbits and foxes together, so that foxes can eat rabbits. And on the other hand, we assume that foxes would just become less on their own. So there's the negative factor here on the, depending on the foxes, on the population size of the foxes themselves. So this is our system, and we can easily write it in differential equations by using such an helper function where we write the derivative on the first parameter. So this is the standard approach where we model these different x and y just by writing to this array. And here we use just a double equal to give it a name for better readability. But you can, of course, leave out this intermediate one. We have our state, which is summarized by u, and we spread it into x and y. And we have a parameter vector, which are all the nice Greek letters, and then define our functionality here. So just if you haven't known, so there's always the possibility to use Latex syntax. So I now had pressed backslash and alpha, and then I pressed tab, and then I get the nice Greek version. But you can also just copy and paste them with UTF-8, so it will just work. Just a normal character, just not so normal in the sense. Okay, we have a starting condition, we have a time span, and we have our initial parameter vector, which is just there from literature. And we can solve this now by using the solve method. And we see the blue one is now the rabbits, and the red one are the foxes. So we see that the rabbits, they increase in population. And if the population is large enough, then the foxes come and grow themselves in population, eating more and more rabbits. And we see this nice shift in the cycles, which are just a consequence of these differential equations. Yeah, you can really easily imagine what's happening with your ecosystem. Okay, so this should surface as an intro to the differential equations package, and now let's combine them. So the first part is that we just may want to learn a differential equation just like we learned our neural network. And this is the first example here. So this is one big cell so that it's meant for being easily re-executed, but let's go through it. So what do we import here? So we import Flux and the package DiffEqFlux, which is now the glue between the Flux neural network package and the differential equations package. And we also, I repeat these important imports every time. We also use the differential equations package here. So we have our initial parameter vector, and now we want to use Flux, and we call our Flux params function on them. So there's now, now intense network structure here, no implicit parameter handling, but still the same approach works. We formulate these as our Flux parameters, which we want to optimize. Then we have a predict function, which we then in a second put into our loss. So predict would be kind of in the normal setting just a neural layer now, or a complete neural network. And instead of kind of having a dense layer or something, we have our ordinary differential equations package. And we put a problem from above in. So this is just really the same solve like we've seen above. It's really the very same. And in addition, we apply a couple of extra parameters. And yeah, and the second one, just that you know, this is the ordinary differential equation solver. This is the recommended for, I would say, standard problems, and technical terms, non-stiff problems. And yeah, you can also check it out. I opened it here already. So on the documentation of differential equations, there's also one for ODE solvers, and the recommended one for non-stiff problems is T-SIT5. And yeah, we have the same also for stiff problems. So yeah, in case you experience bad performance, just it's good to know that you can try out different solvers here and you get different performances. We put in our parameters, which we're going to update, and we also need kind of to fix our output, and we do this by saving it every 0.1 second. So we have a time window from 0 to 10, and this in total then, how many time steps are there, makes about 10 steps. Not 100% sure, but yeah, should be 10. And we grab our output. This is just then implementation detail. There's kind of the information there. Okay, and then we have our loss function, and we do this now by just comparing. Totally simple. Yeah, we use an absolute difference, and it's already running. I need to re-execute it in a second. And we compare our prediction against a constant one. So you may have already seen the simulation below. So it forces it to be constant. This is just, for example, purposes so that you can see kind of that it learns something. And in the sense what we've seen before, so this was really our target value, yeah. And yeah, instead of this target value from the data, this is now forced to 1. And we now again learn, and we learn now in a different way. So you've seen them both. We have a data, which is just pseudo data. So it's an empty tuple repeated 400 times. And we have an optimizer, this time here, Adam. And we have a callback function. The CB stands for callback, which is then plotting our system. There's a little helper function here that's called remake from the differential equations, where we can use the same ordinary differential equations problems, but place new parameters on it so that we really see the update. And yeah, and here for these callbacks, I always like the show inline flag. And now we call the callback once to just have the initial picture. And then we call the training loop. And this is the alternative. Before we've seen kind of the explicit loop, and this is in the sense hidden behind this helper function train, where we just put the loss, the parameters, the data where we iterate upon. So yeah, there comes the for loop then, and the optimizer and an optional callback function. Okay, so if I re-execute this again, we spare a couple of pre-compilation stuff. And yeah, so it's much faster now. And you see that the thing is going to be more and more constant. I just repeat it one more time. So we start with a normal Lotka-Volterra equation, and now we force the rabbit population to be 1. And because of these two are being tied together, the rabbits and the fox population, also the fox population gets down to 1. So I'm actually not sure whether this makes sense biologically. If there's one rabbit, okay, there's probably kind of because we are having a continuous system, this doesn't account for the discreteness of the system. Okay, so bottom line is that as we've been learning now the new ordinary differential equation through the Flux ecosystem, we could also just place it as one of the layers of our chain. Yeah, so important part is just to keep in mind that you have enough output parameters. So the save at needs to be finely tuned. You have the starting point and the end point, and the save at, so you get the number of output values. And then if you have this in mind, just put it as part of one of your layers. So you can have kind of a recurrent neural network before, and then place this ordinary differential equations and put another layer on that. Just combine it like you want and take the derivative to everything. So what's the timing? Yeah, I think we are still in time. So this part is now kind of the alternative. We forced it to 1, and now we would like to force it to match kind of a sensible Lotka-Volterra system. Yeah, so this is kind of your little task now. We want to create some true target values and then fit our neural our let's still call it neural network to the target data. Yeah, so the key part which needs to be adapted is this loss function. Just copy and paste it here. So we somehow need to get a y in here. Okay. Here I see kind of the point which I jumped upon above a little bit quickly. So just take the first output. If we would have if we just solve the system, we get several outputs. And yeah, so this is our U, this is our output, the key output vector, which we can index. And if we take the 1, we get the rabbits. And if we get 2, we get the foxes. So this is really forcing the rabbit population to 1. What I've printed here now is just like one way to realize some data is just to take the initial data and learn backwards in a sense. So if we place the p-values which we learned, it looks very, very similar, but it's from 0, it's really tight between 0.9 and 1. If I just leave them out, we have our original timescale. So hence I'm going to use these values. Okay, this should actually. Why not defined? Okay, so you kind of have seen it. Still looks like not super easy. So I think we would be simpler if we take a couple of other parameters. Target value. So let's just create some random parts. And there's this part. Okay. That makes for a lot of foxes. So I hope the idea is clear that this is very, very easygoing. Yeah. So what's important for me is that you have this feeling that, okay, this is hackable. Yeah, I can do whatever I want. And this is no real magic here. I can use the packages in a super flexible way. So what I've changed now is really just I made a copy of above and changed this line so that I, instead of comparing to 1, I compare to my train target values, the y, and have my prediction now as the x. I made sure that they have the same number of elements. I'm using the same save at and the same ODE problem. So that's easy. And now I just use the sum, which may be a bit more intuitive of, yeah, the direct sum. In there, I have kind of a for comprehension. So within the sum, which saves a bit memory, but yeah, it's important. And take the absolute squared value. Yeah, and can differentiate through this. Okay, so we see it learned the y limits are not super intuitive here. So yeah, now it's already learned. Interestingly, we seem to reset some parts. Yeah, we reset to the starting parameters here. This is the reset, and we then learn the new parameter set, which we put into our train y, which is this here. Okay, so that was the first part of the scientific machine learning. So we now put an ordinary differential equation just as one of our layers into our neural network. So this is really straightforward. Every layer in Flux is just a Julia function, which can be differentiated, and an ODE system is just like that. And you can also now use other differential equations here. So check out the further links then at the bottom. You have delayed differential equations, stochastic differential equations. I guess algebraic ones work too here. So it's really kind of the full support for whatever differential equations you need. And it just, yeah, the ordinary ones are the easiest to use, but the support is there for all of them. And I myself, of course, I'm very fond of the stochastic differential equations and very, very much like that they are supported as well. Okay, so then let's go to the second part. This is the other way around. Now we put a neural network within our differential equation, namely to model the derivative. Okay, so here there's a little example from the tutorial, just to see it live in action. A little bit adapted for easier, so that it can be read easier. We have just a little matrix which we combine with the cubic value of our system, and this is our derivative. So we want to plot this. Where comes the plot? Okay, first execute a couple of lines. Just back to the first cell of this section. So it's really just define in another differential equation. And we have another time range and initialize our system. Yeah, so the time range here is this one, and we have then a specifically set point, a set of time points where we solve the system for. So you see before we've made time steps, sorry, and here we just specify the whole range beforehand, and this makes it easier so that we can set the length of the output. Okay, so we just solve it, and then the last step, it's easily forgotten. Just the solve outputs like a more complex data structure with a lot of more information in it. And by wrapping it into this array constructor, we really just get the output of the system U. Okay, so the second part is now to define our neural network, which then should model our derivative. And as before, this is really just a neural network. And now the cubic value makes sense. Yeah, we have another dense vector with a tangent hyperbolicus activation function and another dense vector at the end, a dense layer. And we put this now into our ODE by using the helper function from the differential equation flux, which is just called neural ODE. And you have, as you can imagine, similar helpers for the other differential equations. So it's again the definition of an ODE. So we put the time span, the solver, our save at parameters. Yeah, we can kind of place a couple of extra configuration and have now N stands for neural network in this part, our neural ODE. And we can use again flux on top of it. So this works. And what's also nice, it's really just a function. So this functional aspect of things is also here valid. And take the prediction of the neural network. So for some reason, I placed a semicolon here. Let's really look at the prediction. So yeah, we have then our U value, which is then the final prediction. So we can again put this into an array and see that we only get the metric similar to above. Okay, so this is a little plot of the data and the prediction. And we see as of now, it's really far off. So as with all of these examples, we want to learn. And yeah, and here we define now our loss for this neural ODE again as a sum of the original data and our prediction. So here we have our starting point. Okay, so let's just run this directly so that we see where we start. And now there's again a standard flux training loop. We here use the flux train operator again for simplification and have another callback function which just plots again this part. Yeah. So the approach is similar to before. We have a pseudo data with an empty tuple so that our implicit parameter handling gets called again and again and again for 100 times. And yeah, have our callback then, which really prints it. So as you see, okay, nothing happens. So we are still in compiled time. And then in a couple of seconds, it will start learning. So yeah, we just have 100 iterations here, but yeah, this is enough to see that it really fits. Yeah, and an important part is that we really just fitted the we fitted the derivative of our system. So we didn't fit the system directly. Yeah, we are printing the the normal system here, but what we're going to fit is really just the derivative. Okay, so now there's really the point where things need a bit longer for compilation. Okay, should start in a couple of seconds. So yeah, my little task now for this section for you is to try to fit our original system. So it would be nice if we can learn our rabbit and fox's relationships with our neural network. And yeah, let's see what we need to adapt there. But it should work. So it has also two outputs. Like before, we can now interpret this as rabbits and foxes. And yeah, now it works. Okay, I got the point. So here you see that it now learns and adapts the gradient, which then affects this final system. And this is, of course, generic model. So using these neural ordinary differential equations or these neural differential equations, you really have a powerful model to your hands for modeling time series by not modeling the time series directly, but the differences on a continuous scale. Okay, so let's give it a try then. Yeah, let's see kind of the loss. We started really with about 300 and we ended at 1. We just have 100 iterations, so we can continue learning here. But still, yeah, you see the improvement, like, yeah, standard learning. Okay, let's give it a try and let's learn the original data, the rabbit and foxes data. Okay. So I'm just copying kind of the essential code, which is the loss. We need to adapt this for sure, and the learning part. But I think for simplicity, we can reuse the same neural network. So I think this might have been the hardest part. So we need to get the data from the beginning with the same time steps as we've been using now, so that we like, it doesn't have to be the same time steps actually, but it just needs to be the same length. Okay. Okay, so this should now be better. We have a couple of timestamps here. Okay, so maybe that we need to increase the data size. Let's see. Yeah, but this now gives us a lot of control. So there's the ODE2 data versus the ODE data. So it could be ODE1, but I leave this out. And I already changed it here. So this was ODE2 data. And I compare it to the other one. I just leave them the same. And let's try whether this already works. Ah, yeah, okay. So the prediction doesn't make sense. Okay, let's try to interrupt. Okay, interrupt worked. So we also need to change the prediction part. Okay, so yeah, as I thought, it's a little bit sparse. So we see kind of our regular, our cyclic behavior. Not sure whether this can learn it actually. So a good question what it needs right now so that it that it doesn't learn. Okay. Don't know. As before, probably need to be a bit patient. Okay, so you may have tried it out as well. So the general idea is again just replacing our target values. And here, as before, we need to make sure that we have the same data size. And yeah, but now we compare output of a differential equations on the one side against another output. Ah, now it starts learning. Yeah, and it also might be that just having 100 iteration are by far not enough for this task now. And I think this is where we are. Now it's still learning. Yeah, so you probably need to play with the number of data points. Yeah. And with every learning, yeah, so you need to check whether it was successful, whether it converged correctly. Yeah, it would be nice to run this in the background and really see for a longer training period whether it's able to capture this on the fly. It's just this simple neural network. Okay, so we just adapt the target values again and can, of course, start learning and try different neural network layouts. You can also, as before, combine other parts in the derivative. Yeah, you don't need to use neural layers. You can also use functions as we use them. So this might actually also complicate things because let's take back. Yeah, we have a square function in the beginning, which was very much fitting our special case, but it's now super hard probably. Yeah, this may be one of the biggest reason why nothing is happening. Okay, but you get the idea. And this is kind of the important part. So this is easily hackable for you. And of course, machine learning has this try and error part until you really find the good fit between the neural network and the data. To finalize this part, just a little screenshot from the paper Neural Ordinary Differential Equations from the NeurIPS presentation. So it's quite old compared to machine learning standards, but it gives you an alternative view, which I find quite helpful if you haven't thought about this before. So there they motivated this type of models with residual neural networks, where your key structure is a bit like this here on the top. So you have a couple of layers. They are discrete. So we have H now as the layers. And the next layer, the HT plus 1, is defined as as an addition to the layer before, where the difference, this addition, is now defined by our neural network. So we get the inputs of the layer before and our neural parameters and learn our function. And these have been very successful. And the neural ordinary differential equations is in the sense a continuous version of this residual network. And I also very much like these two pictures here. So in the residual network case, you have these discrete layers and need to be precisely on the discrete timestamps. And then the ODE network, there is no discreteness involved, at least not on the modeling way. Of course, the solver you use, it will sample your differential equation, but it can do it in an optimal way. And different solvers do this differently. And there's a lot of work which went into this direction so that you really have an optimal subset of points where you sample. And on the other hand, it's also easier to get precise timestamps in. So if you have kind of time data which doesn't fit nicely into such a well-defined time step grid, you can use an ODE nevertheless. So you just combine the timestamp information with it, and then the ODE will handle it. As you've seen above, we can really specify in detail which timestamps we want to sample at. There's no problem at all with it. So this is a really nice advantage from this perspective. And check out the paper. I also made a link below, I hope. But anyway, you can just Google it. It's super popular. So there are also other applications for just this ordinary differential equation network. Another nice characteristics. Also, for probabilistic modeling. Okay, so that is the part here. So as now thought, our neural network is not able to learn our original equations. But sure, it's not far away. Just need to tweak a little bit here and there, and then it should be able to get this back. Okay, so almost, kind of half an hour left, a little bit less. So I'll move on. First one leaving. Thank you too, Valerio. Okay, so this part is now one of my favorites, actually. So I've been using the Bayesian estimation quite a lot, and it's awesome to see that this can be combined with differential equations as well. So let's have an intro to Turing.jl. We already had another speaker from Turing.jl in another Julia User Group Munich session, but here like a little mini example. So we now use the Turing package, and I just execute this. What does it do? It uses Bayesian probability theory, and so we start kind of with some so-called prior beliefs, some some thoughts about how the world might be, but still in rough terms. Then we get data in, and we want to update our beliefs, our thoughts about the world, so that they better represent what we actually seen. And usually, if you've seen some data, it's not the case that after seeing some data, you know for sure things are this or that, but yeah, you just are a bit more certain than before. And yeah, this little example illustrates this nicely with a very, very easy example. So what we do here is we generate some coin flips. And yeah, so we have a probability value of of heads in the coins. Okay, thanks documentation. And we have a number of times which we iterate. So we do this a couple of times, and this is kind of our learning. So we see a lot of coins, and we want to understand, we want to see, okay, what's the probability of heads? Yeah, so this is the task. We generate our random data, so with this number of points here, and we use this Bernoulli distribution, which is in this regard really just 0 or 1. Okay, now comes the Turing model. And we have this macro here in front, so there's a little bit more magic involved here, but still really flexible, as you see in a second. So the syntax support is awesome. So this model macro gives us access to a special operator, this tilde, which says that something is distributed like on the thing comes on the right. So the better distribution is now a really good distribution for a probability value. Yeah, so if you had kind of this Bayesian estimation, these are really standard distributions. Just kind of get your crash course in Bayesian estimation, and then you know that beta is the distribution you want to choose for your probability. And the parameters are actually really easy to understand. This is the number of what's the opposite of heads? Okay, so this is really like you have seen a couple of zeros and a couple of ones. And this, yeah, like if you made a test before, okay, I've flipped 10 coins and we have 10 heads, then there would be kind of a 10 to 90, yeah. So that would be our prior beliefs. And because we don't know nothing, we just have really small certainty. We just have seen everything once, so to say. This is our prior. And then we model our data. So the data comes in and we really use kind of standard user functions here. We get the length for it and we make a for loop and we model every single cell in our array as just this Bernoulli distribution, which we sampled from. So this is kind of a nice thing. We can sample from the same thing and we can also use it for the modeling part. The probability now is itself has a distribution and we want to update this. Okay, let's take a look what this does here. So we have our probabilistic model and we sample from it. So we really just call our model coin flip on our data, which we generated, and we sample for it with Monte Carlo sampling. Oh, okay, so this might have been also the case for you. So this is live and using the same Jupyter notebook as you have been using. So my connection just broke down, probably because I've been just not clicking too often. Computation was too long, but there's no problem. So these things are made to easily reconnect, and this is the button at the top. So the launch binder will open the notebook again. Of course, the pity is our state is lost. So I will leave this open now for if we need to kind of copy something. Yeah, so a little re-execution. And I think I just need the standard Lotka-Volterra equation. We're going to reuse that. And the other parts are not so important here. Okay, so this took some time. Okay, but then let's maybe jump back to the output because we just had it. Okay, so I can explain you the output, what you see here. So this is kind of a standard part in the probabilistic modeling, the Bayesian probabilistic modeling. We usually can't find an explicit solution. So in this case, we actually can, but in usual cases, the model is too complicated and we need to sample it. We use a Markov chain. Yeah, and here we see kind of the chain. So this is really kind of an algorithm which jumps back and forth, and it is like a line which goes through our probability space. And it has the theoretical guarantee. It doesn't work always, but yeah, often, that this really approximates the true probability distribution. So we now see here at the histogram of what we see on the left of this run. Yeah, and we see that it's nice fit where we are actually a little bit off. Yeah, so 0.5 is here. This is kind of our ideal value, but our data, which we've been seeing, actually suggested something yeah, lower, that there's a lower probability for heads. So yeah, my little task here, we have also kind of another histogram plot. I think this is duplication of here, but it was not showing that nicely on my test. Is that this now will be different if we use different number of n. So let's see whether we already there in computing. So if we change the number of n's to 1,000, yeah, we would be much more certain about which probability it really is. And you would see this here in the distribution. And yeah, if we go to just 10 values, we have a much broader distribution and would be far off. And you can see the uncertainty in this estimation. So yeah, the goal of using such probabilistic models is often to capture the uncertainty, so that you know, okay, I learned something, but actually what I've learned, yeah, here I'm good, I learned quite well, and here I learned not so well. Yeah, so I should be a little bit more hesitant to really interpret the results. And this one application, okay, I'm back. So the new notebook computed it. So let's give it a try. Now I can get 1,000. And yeah, so the sampling takes, yeah, okay, it was mouse compiling. So we have now 1,000, and you see we are much more centered. And let's 10,000. We get even, yeah. So we get a steeper and steeper probability curve. And if we get down to 10, we are not so dependent on, yeah, so we get a much wider distribution. And interestingly, kind of now we see that in the middle, yeah, we really get an estimate, but because of the nature of the data, it really might be shifted. And this is what might happen to you with your real data in your case. Yeah, you learn something, and just because your data is random, you learn something else. Yeah, so this is pretty far away from the 0.5. But yeah, we still capture it in the uncertainty, so that 0.5 is in the sense a possibility. Okay, so enough for the introduction to the Turing. And now we see kind of Turing in action on our Lotka-Volterra data. So I really love this example. So what we're going to do is we just learn on the foxes, and we're going to also, of course, because the system is interacted, learn the rabbit population. But we'll see that the uncertainty in the rabbit population is just much higher. So what do we do here? We again have our initial ODE problem. That's really from the very start. I re-executed it already, so it should work. And we save it again at 0.1 timestamps. And what we do in addition now, our data is now computed by the data which we got from our solution, plus some noise. And this we're going to plot so that you see what this means. So what we're going to plot is the differential equation system itself. We see this as the lines, and as the scatter plot the points, we see our noisy observation. So we also have kind of some randomness involved here. Okay, so we can model this. We have noisy data. We assume we only have the Fox data, the red one, yeah, and still we can learn from it and get a good idea what we've learned and what we haven't learned. So we use Turing and differential equations. We combine them now, and we have a fit Lotka-Volterra where we get our data in and our ODE problem. So this really is now just another parameter to our model, and we can use it within. What do? We have our alpha, beta, gamma, and delta parameters, and we just kind of take them as normal distributed, but we truncate them. So as you know, these are all positive. So and in this little example, we realize this by truncating the probability distribution to this sphere. So it will renormalize everything. So this is a true probability distribution, and really nice to see that you can do this. Okay, so then we have kind of ranges of our parameters, which makes sense biologically. And we solve our ODE problem by just putting in our parameters. So this is now distributed after probability distribution, but we can really use them as normal parameters. So it's awesome interoperability. We again save at our timestamps, and now we have here, before we had kind of done this one, and now there's kind of another approach here. We can also, if we know that, use this keyword argument, save index 2, and then leave out the indexing. Okay, so in addition, we now, our data was normally distributed, and we also put this on top. We have a standard distribution for the variance. So here the sigma, the standard variation. This is, we can use an inverse gamma for that. As always with this approach, you need to have kind of a little intuition. Okay, what are these parameters? But they're standard approaches, or you can print them. You can take a plot of them and see, okay, makes roughly sense. And then we model our final data, which we take as our input. And we model this at multivariate normal. Our predicted, there we now need to access the U value. This is the same then as array, probably. So we did this before. Now we access the U value directly. And we have our variance, the standard variation squared, times an identity matrix. And so this is just explicitness. Don't need to do this. And we solve our model. So we call our model with the data, and we only put in the Fox data and our ODE problem. So this just compiles the model. It doesn't do much. So it's a pretty big thing. Not so important. And now comes the point where we look what we actually going to learn. So here's again the sample as before, and we now use the NUT sampler, not the, before we had the HMC, the Hamiltonian Monte Carlo. And we use a NUT sampler. It's quite common and works very well. And we have the MCMC serial here, kind of some parameters. I myself need to get a bit more into depth here. What are the concrete options? So this is taken from the example. We have each chain has 5,000 iterations, and we have three chains, sorry. And and now having these chains, they are really the same as we've seen before. So here this is a chain. So one of the sampling iterations. And now we use kind of these parameters to sample from them. This is our distribution. And we sample now 300 examples of our parameters. So they are called posterior samples just by having, this is the usual name, prior versus posterior. Prior is the thing which we start with, and posterior is the thing which we have after seeing our data. And now we plot them. So we solve our differential equation problem with these parameters. So for each of these parameters, we plot our system, get a single line. So this is a light gray from the color so that they stack up because we have 300 of them. So we see the distribution. And finally, we also plot our original solution and the data. So let's see what this does. We need to wait a bit probably, but don't know. Let's see. Yeah, the NUT sampler is new, so this needs pre-compilation. Yeah, I think we need to wait for a couple of further compilation steps. Okay. So this is kind of the yeah, most impressive part of combining all these learning algorithms with differential equations. The downside of these probability methods is that they take a bit more time. Okay, so we get a couple of warnings in the middle. So the simulation rejected a couple of solutions because of numerical errors, but realized this on its own. So this warning is a feature. Yeah, so the probability modeling, of course, takes more resources. Yeah, if you just learn your neural network and learn, yeah, what's sometimes called a point estimate, this, of course, is faster. Yeah, and if you use the probabilistic way of doing it, you need more resources, but you get the uncertainty. And depending on your use case, this is really crucial to know your error and, yeah, to have a better understanding of your model. So this is learning now, and despite it rejected a couple of solutions, whoops, now we jumped into a subset. We're going to see the final output nevertheless. So all these warnings, they appear while learning. Of course, you could turn them off to speed up things, but still you see that already this little example takes some resources. Yeah, so this is just normal part. Okay, so now the sampling is done, and we have the plots probably which are generated. So all the solve calls, we solve the ODE problem now 300 times and plot things together. Okay, so because time is also rushing towards the 8 o'clock. There we are. Perfect. So this is our final output. You may have it yourself on your system. So we see the original system as before. Yeah, the blue line, it's a bit small. It's a bit more in. And the red line with the points which we saw. And we've learned depending only on the Fox data, on the red data. And you see nicely, it's still a bit small, but yeah, that the gray lines in the background, these are our samples from what we've learned. Around the Fox data, there's a pretty small margin. So you see that it very, very much learned the system. And yeah, remember there is in addition some random noise on it. You see it especially here, but we've been able to really make a good approximation. And the rabbit data we haven't seen at all in this learning process. And you see it awesomely, yeah, that, okay, our trajectories, our example trajectories, they really show a lot of variation in the modeling of our rabbits. So yeah, this approach is sometimes called data retroduction. What's this? Yeah, let's give me the right name. Data retroduction. I don't use this often. So that we have our model and yeah, represent it in such a way that it fits our original data, and then we can easily interpret the variance here. Yeah, sampling is just a good way, an easy way to get such nice plots. Okay, so last little exercise. It's really super simple, but yeah, more like a side note. These Bayesian estimations, sometimes they don't converge, like similar to neural networks. But here we actually have a good way to check whether they converged. And yeah, and we already saw this above with our chain. Okay, this is not how we call them. It's just called the chain. So we have 3 chains in this chain. And yeah, if we plot them, before we just had one chain, now we have three chains, and we see what we've learned, and we see the three chains being plotted here. And yeah, they look a little bit different indeed. And if they are kind of completely different and we don't see kind of one similar thing, then our convergence is relatively bad and we need to tune some parameters or simplify the system. And we also in our data here see kind of quite different fits. Yeah. And the more these three chains are kind of similar, the better we know, okay, our sampling process has already converged. And this is quite nice and an easy investigation to see, okay, we've done well. So here, there's a little bit offset, but might still work. Yeah, we may want to increase the length of our chains of our sampling. So this gamma value looks a bit better. Yeah, similar for delta, and the sigma, it's a bit off. Okay, so I want to show you that here we really have kind of a standard inspection to see whether things have been converging. And and we also see the nice results in the rich reduction plot. Okay, we are approaching the final end. Okay, so I just have a short note that there is some support on not only fitting neural networks to data, but also fitting symbolic expressions to data. So here's just a super small example where we don't use differential equations at all, but we just fit a standard square function. And just to give you a feeling, okay, this exists and you can do this. So we use here symbolics. There's in the SciML system, the model toolkit and symbolics. There's support for not using numbers, but formulas. And you get a couple of advantages like better performance optimization because the system can be analyzed automatically for you. And you can also do stuff like here, like you try to learn a symbolic representation of your data. So what we have here is really just an example from this squared function. We can use broadcasting to generate some example data. We define this as a direct data-driven problem. We define our variables in a symbolic way. We define a basis up to the power of 4, just for an example. We need to wrap this into a basis where we have our equations and our states. This is now just our u state variable, but this can be kind of multiple variables. And then we use again our solve. So, but instead of solving the system now for a solution, we solve it for a basis. So it will try the combinations of our basis vectors and find the solution. This is of course totally simple now. So but nevertheless, you get the idea how the system works. And we can print our solution. We get a couple of statistical measures, how good we've been fitting. And and we can also see the result. And in this part, we get back, okay, our problem is indeed quadratic. And you can put this as part of differential equations. So this really lives in the scientific machine learning ecosystem. And you get a lot of further functionality there. Nevertheless, it's a bit advanced, and so if this is your field, that's probably perfect that this tool is part of the toolset. But if not, the other parts, what we've seen before, they are, I think, a bit simpler to get more into the Flux neural network system, the Turing probabilistic modeling, and the differential equations themselves. Okay, so I've summarized some further material here. There's been another tutorial to get into Flux. I really much like this. There's a blog post from Differential Equation Flux. That was one of the main sources. There's also documentation, of course. There are 2 papers. Let's see, maybe we have some time in the after work to look into this universal differential equations paper. So this one is from the Julia folks. The other one was presented at NeurIPS. And there's the tutorial for the Bayesian differential equations, where there's a little bit more. So we can also combine the the probabilistic modeling with stochastic differential equations and delayed differential equations. So there's a lot more to see and to combine. And yeah, and finally, there's also the data-driven symbolic regression part. And for simplicity, I directly linked a linear and a nonlinear ODE example so that you have an easier entry point, because the documentation might be a bit overwhelming. Okay, and with that, I want to thank you for being there today with me. There haven't been much questions in the meanwhile. I hope this meant that you've been following intensively. And yeah, I'm really thankful that you're still there with me. Quite a lot of people. Yeah, so thanks for listening. And as always, my founded company, Julien.io, is always looking for cases where we can spread Julia into industry. If you have a good case at your company or know someone else who might need help, reach out to me. Okay, thank you too. Thank you for your kind words. Yeah, I know there was a lot of extra material today, and I hope I still could give you like one red thread to again see this Lotka-Volterra example. And I especially like that these three different packages, the flux, differential equations, and Turing, can really be combined that flexibly. So for the ones still there, so just that you've seen this, so this is the universal differential equations paper. And this is kind of, again, yeah, it's a bit harder to digest probably than what we've seen today. Nevertheless, it's kind of the reference where they say a couple of extra things about the Julia ecosystem and compare it. And just because this is then again easy to digest, this kind of one table summarizing the advantages of the SciML ecosystem. You have kind of support for so-called stiff differential equations. So in our sense, it's kind of a little bit harder in simple words, and you need a bit more effort to make them work. You have differential algebraic equations, stochastic, delayed, and there's also kind of effort to stabilize everything numerically. And you see that this is really kind of unique compared to all the others on the field, mainly in the Torch ecosystem, but also in the TensorFlow. And you have also GPU support, yeah, and you can also run it in a distributed manner. So there's really a lot which you can use under the hood, and we just looked into the very beginning here. You can combine a lot of things. And then there's a second table here, which compares the speed, which is also interesting. And yeah, and the most important thing is that the speed up, so yeah, smaller is better here. And you see that especially this is a number of ordinary differential equations which are linked together, especially for small problems. The SciML ecosystem is really beneficial, but also for large problems here in this benchmarks, there's still a huge speed up. But yeah, the smaller your problem is, the more advantage you get out of the Julia ecosystem. Yeah, so these two tables I appreciate very much. Yeah, good summary. And there's a lot of more detail, like what you can do with these special cases, yeah. That you use other differential equations and combine them. So this paper is a bit harder to digest. The other paper from the neural differential equations, this is relatively easygoing. And yeah, so you can also check this out to get a bit more a feeling of, okay, what you can do with this combination. So this was the first one in the series. There have been a lot of other things going on. Yeah, relatively easy to digest. Yeah, so thank you for being there again. Have fun with the Jupyter Notebook experience. I'm very, very thankful that this binder initiative exists So this is a binder notebook, which is sponsored by a lot of awesome companies. And this makes it possible that we have this hands-on experience so that everyone has their own notebook and can experiment further with the code. Then I wish you a great evening and thank you for being here today.